Copter and quadcopter indigenous drones, where we ask students to assemble on their own on different problems and different specs. And the second vertical we have in the 3D printing, we have got SLA printer and also FDM printer in our Idea Lab. The third vertical we have is the IoT ESDM board designing using PCB prototype machine. We have got both manual and as well as the laser one. So where we allow students to convert their ideas in the form of circuit schematic, and they can simulate and they can test, and then they go for PCB implementation. So this is the three flavors we are currently, and in future we would like to extend this with AR/VR technology for CS and IT. Once again I welcome to our Atal FCP program. Listening to you because we have invited, mechanical department has invited a couple of times for FDP programs, and myself and Dr. Rajesh Shah, we invited for one of the AKTU BOS meetings. So your active involvement, discipline, and you are a role model for all of us, sir. Thank you, sir. Thank you very much.
Robotics, and many of the audience have also heard. For them, it may be a boring session also, right? And for the newcomers, probably I can give some fundamental aspects of robotics. Okay, we have conventional way of doing things, and we are going in for computer-assisted doing things, that is in the form of automation. And apart from that, there will be robotics into that one. And as on date, these two are being coupled with the implementation of intelligent system in these man-made systems. If we effectively bring in these kind of implementation, automation, robotics, intelligent system into every aspects of activities, then definitely we can achieve all this Industry 4.0 and other concept in reality, okay, which will enhance the productivity and cost effectiveness of manufacturing and many other things, right? So friends, here my focus area is exclusively on robotics, right? And it's a faculty development program, mainly for we as a faculty members, right? So as a faculty member, my focus area is like to draw your students to the field of robotics, because students are more interested in this field, robotics, AI, and all those things, right? And to bring in those students to involve in projects, as Professor Sampath Kumar was telling, that you had a laboratory, just now I saw there like some quadrators and other things have been designed and developed. Yes, this is the area where when a student gets an hands-on experience, he can build a career. Ultimately, the goal of we people as teachers is to bring in a good career for our students. So this is the area, one of the areas where we can put our efforts in bringing interest in the students in the field of robotics, automation, and intelligent systems, so that their career will be built up. In the process of that, we will also learn plenty of things. With that in mind, I planned my lecture session in such a way that I'll start from the fundamental aspects of robotics, then about different classification, basic elements. Then I will switch over to one of the most important activity in robotics, which is known as robot arm kinematics. I'll tell you about how exactly you can address robot kinematics problems and what is the need of it in the first place. Then we'll be looking into something on trajectory planning, which is another important activity in robotics. Then sensors, then dynamics problems. So almost every aspect that is related to robotics will be taken up in a very brief thing, like just to give a fundamental idea about it, and then to go about how exactly you can go about in implementing of that. Right? So robotics, the very concept of robotics started way back in 1920 with Karel Capek, who is a Czech playwright, right? Okay, through his Rossum's Universal Robot. We need to remember it, right? Every textbook, when we refer to robotics, you will find this information. So it's a way of expressing our gratitude. We need to cite this name, right? But the very or replication of a human operator in the form of a mechanical system comprising of links and joints. Now I've got a series of links and joints that won't function, that needs power. So that is where, if you want to give motion, I've got a joint, I need to give a drive system. So now I can have a mechanical drive system, electrical drive system, hydraulic drive system, or pneumatic drive system. So depending upon the application area, I'll use a drive system. Now look into this man-made mechanical system, which is comprising of series of links and joints with drive system. Okay, now this needs commanding signal. So that is where we go for the concept of computer numerical control, right? We use computer through programming, okay? We're going to send the programming instructions, convert it through its hardware and software interface. It will be transformed into equivalent control signal, which goes to the drive system, and they will go to operate. So ultimately, the objective of replicating or replacing a human operator with a man-made mechanical system has been designed and developed. That is nothing but robots. This is the actual robots in industry. Okay, so industrial robots are comprising of this kind, right? So these are the CNC machine tools which came into existence for more precise and accurate manufacturing, which can be controlled through programming. That was CNC lathe, and this is CNC milling machine, which is known as machining centers, right? So these machine tools are required for the purpose of manufacturing, right? For removing unwanted material and then manufacture. Yes, I've got an automated industry, which is relevant for Industry 4.0, and these machines have been arranged in an order, okay, around the operator, and operator was loading and unloading the work common. That's what you can see here, right? Raw material will come here, you will load it onto the first machine. Then once the operation has been completed, the machine will stop. You will take the component and load it into the next machine. That will run as per the CNC programming. The process continues. And at the end, you're going to get a finished product or a semi-finished product. Okay. So here, this is the point of concern, right? The activity which has been done by human operator will be carried out by some mechanical, man-made mechanical system, which we call it as industrial robot. So this is the place where the concept of robotics came into existence in the industry. So this is what I was talking about. This is the gentleman who gave the concept of it in his playwright. And this is the Robot Institute of America definition on robotics. It's a reprogrammable, multifunctional man. That means you can do plenty of activity, jobs with the same system by just changing the end effector. So these are the major components of it. Okay. This is one of the basic structure of an industrial robot, which is very widely used in industry, which is known as articulated joint robot and jointed arm robot, which is an imitation of the human. There's a body, there will be upper arm, there will be lower arm, and then there will be hand. So that you can make out in this one, right? And it has got different degrees of freedom of motion, right? I made the mechanical system comprising of body, arm, and I provided the joint. I've given the drive system. Through computer, I'm going to give the control signal for its motion, right? These robots have to perform something in the industry, okay? So now this needs to move, okay? So if it has to move, then you have to provide joint, and each joint is going to give 1 degree of freedom of motion. Okay? In this one, if I provide a rotary joint at my base, I can able to rotate my body. Okay? That is 1 degree of freedom of motion, with which the rest of the thing can have an access anywhere here. So one joint there at the base, if it is a rotary joint, okay, then you can have a rotary motion, 1 degree of freedom of motion. Then from the body, upper arm, right, there's another joint which can give this kind of a motion, right? This is another joint, now 2 degrees of freedom of motion. Now from upper arm to lower arm, I've got another joint. So 3 degrees of freedom of motion. Otherwise you can't execute any task. And finally, to the hand of the robot, okay, it has got 3 degrees of freedom of motion. You can be able to make it to rotate like this, which is known as roll motion. You can make it move like this, which is known as pitch motion. And you can make it move like this, which is known as yaw motion. So what to do with this one? I got 3 degrees of freedom of motion, axis 1, axis 2, axis 3, associated with the this particular thing, you can enable it to reach the desired position in its three-dimensional workspace. That's a requirement, right? So that is known as positioning. Then once it has been positioned, the hand of the robot may be somewhere here, but I have to grasp the components at this location. Now it needs to be rotated, it needs to be adjusted here, right? This activity can be achieved through the end effector, the hand of the robot, which I talked about RPY motion. So the RPY motion, rope pitch and yaw motion, can be used for orientation. So friends, here with this mechanical structure, we can position the hand of the robot at the desired location in its three-dimensional workspace, as well as we can orient it so that I can execute the task, right? So, and then all these degrees of freedom of motion, once I take the component with the proper position and orientation, by operating this joint, I can take it to the desired location, right? So that's why the structure is comprising of series of links and joints with different degrees of freedom of motion, which helps in the most important thing, positioning and orientation of the hand of the robot to execute the task. Now these are the various types of joints. It can be a rotary joint, it can be a linear joint, depending upon the application areas, right? And there are varieties of industrial robots, and the classification also goes accordingly. And one of the major classification is based on the physical structure or physical configuration of the robot. This is physical this thing, right? So there are four varieties. One is known as Cartesian coordinate robot. In this case, there are no rotary joints. All of them are linear joints. You've got orthogonal slats which you can make out here. Orthogonal slats which is perpendicular to each other. And we have got three armored body joints which are linear joints having linear motion. With that, what we can expect, which is about the workspace within which it can function. If you have Cartesian coordinate robot, okay, 3-axis this one, you can make the hand of the robot to move in a cuboidal workspace. Okay, the workspace of the work region within which you function is in the shape of a cuboid. Okay, then we have cylindrical coordinate robot. Wherein I got two linear joints. This is linear and this is linear, and this one is rotary. Okay, so two linear joints, two linear motion, one rotary joint, one rotary motion. With this, what you can achieve? You can achieve a workspace which is cylindrical linear. Right? It all depends on the industry application. You may need cuboid workspace, you may need cylindrical workspace, or something other kind of thing. So that's why these classifications, these varieties of robot came into existence. This is known as polar coordinate robot. It's been pivoted here. Okay, it has got two rotary joints. One is vertical traverse, another is rotation traverse. Then you can make the hand of the robot to move in and out, which is known as radial traverse. So if you imagine the workspace within which it can function, it looks like a part of a sphere or a quasi sphere, right? Then the most versatile one, the one which I showed earlier also, which is known as articulated joint robot or jointed arm robot, in which all 3 degrees of freedom of motion associated with the arm and body is rotary in nature and rotary motion. Now again, the work volume is part of a sphere, quasi sphere, with more versatility. What I mean by versatility is, as a human operator, if I want to access this particular component which has been in this position and orientation, with this articulated joint robot, I can hold it something like this. The same object I can hold like this also. This kind of a flexibility is there with this configuration, which is known as articulated joint robot. Right? So, friends, with this, what I brought to your notice is that when we are talking about robotics, we are talking about industrial robotics, okay, which is direct impact and industry 4.0 and other kind of a thing. And in industry also we have got various application area, and that is where, depending upon the work region in which it has to function and the flexibility that is required in an industrial robot, we have got these 4 varieties of industrial robot. And most of the industry do use the last variety, which is known as articulated joint robot. Now this is the work volume, right? For Cartesian it is cuboid, then it is cylindrical. This is what I was talking about, quasi sphere, right? Then articulated joint robot, that 3D picture cannot be given, so that's why orthographic projection has been given for depicting the work volume. All this versatility has been brought in this workspace. Fine. So these are the various mechanical elements which are used for giving and transferring the motion. Then as I said earlier, here you can have. So when you are writing the program for this purpose, what kind of an information need to be given? That is the position and orientation information. So here in robot of kinematics, we come out with mathematical expression for positioning and orienting the hand of the robot in the three-dimensional workspace. So what kind of a mathematical expression we are giving here? We use a very simple 4x4 matrix for defining the position and orientation of the end effector. So here, when you are dealing with robot of kinematics, this is even many of the students are doing several projects in this one, right? So they also need to learn this, right? Because ultimately they are even unmanned aerial vehicle, your coordinate and all those things, they are moving in the three-dimensional workspace, right? They need to be properly positioned and they need to be properly oriented. What is the concept behind that? Even the recent launch of Chandrayaan, this thing, right? So it needs to be positioned at the desired location and it needs to be oriented. So there is some kinematics aspect involved in that, and that fundamentals comes from this robot on kinematics. So from industrial robot perspective, there are two approaches of robot on kinematics. One is known as forward kinematics and another is known as inverse kinematics. Forward kinematics, I know the joint angles. Means I know how much this joint need to be rotated, how much this should be rotated, how much this should be rotated, how much this should be rotated. I know this, have prior information of the joint angles. Knowing joint angles, I need to determine the position and orientation in the three-dimensional workspace. If you are dealing with problems of this nature, it is known as forward kinematics. Then there is another situation. I want to deal with an object placed somewhere here with a particular orientation. I know the position and orientation. Now I have to calculate the joint angles so that we can achieve that particular position and orientation, which is known as inverse kinematics. Now, NY frame is nothing but hand of the robot. XYZ is representing the augment body. Now I have got a situation wherein I assume that the origin of my moving frame or the hand frame or the end effector frame is coinciding with the origin of the main reference frame. Physically I can't do it, I can't go solo and physically I can't exercise that kind of thing, but that situation has been depicted. If that is the case, if the origin of the moving frame is at the origin of the main reference frame, how do you represent mathematically? I represent through matrix form, okay? It's coinciding with the origin, okay? Position, where is the position? Along x direction, 0 distance. Along y direction, 0 distance. Along z direction, because it's coinciding with the origin, okay? Position, there is no position information. I've got only orientation. It's not, again, orientation is not coinciding with the main frame, it's with some distance. So how I can express that? I take the components along x direction, y direction, and z direction. Okay, n component along x, y, z, O component along x, y, z, and A component along x, y, z. So that's how I got 3 column vectors. Okay, nx, ny, nz representing the orientation of n, ox, oy, oz representing the orientation of o axis, and ax, ay, az representing the this one. So thus, this position and orientation I have now transformed into a mathematical expression in this fashion. That's a 3x3 matrix. So this matrix is orientation matrix, orientation of the hand of the robot. But actual activity is of what nature? Your hand of the robot should be in the three-dimensional space with proper orientation, then it has to execute the task. In this case, position is 0. So I need to have even position vector also. Right? So now I made a slight change in that one. Now it is no more at the origin of the main reference frame, it is at some three-dimensional workspace, which has been represented through its position vector P. Orientation, I did change. Okay, so the orientation part is this one. This 3x3 matrix is your orientation matrix. No change in that one, but the position changed. It was at the origin, now it is at some location, right, with position vector. So how I can represent this position vector? Again, I take the components of it, represent through this one, Ps, Py, Pz. Okay. For ease of computation, I'll transform this into a 4x4 matrix without affecting the solution, right? 0, 0, 0, 1. One is something called zoom factor. The if you're all from computer science background or other thing, you're then computer graphics and machine vision kind of, even in solid modeling, okay, there is something called zoom in and zoom out. Okay, that effect is through this one, right? One means there is no scaling of this one, right? So friends, with this what I'm conveying is, I told that, like, we need to position and orient the end effector in the three-dimensional workspace for the purpose of executing the task. How do you express that? We are expressing mathematically through this 4x4 matrix. If you have an understanding of this simple 4x4 matrix multiplication, okay, you can deal with any of the kinematics problem related to robotic activity, including that landing of Chandrayaan. The basic is this, right? You need to have this fundamental understanding of positioning orientation. Okay. Fine. With the previous matrix, 4x4 matrix, which is giving 3x3 is orientation, the last one is position, that does not fulfill my requirement. My robot has to function something, right? It has to grasp the component, it has to release it, or it has to do spray painting, or it has to do some kind of a welding. Then this position to orientation changes. Okay? So the earlier matrix was representing the position to orientation. Now I have to bring in this motion, this transformation, okay, which is either pure translation or pure rotation or combination of this. Again, if you're coming from computer science department or other thing, right, in your computer graphics and computer vision, you come across all this pure translation transformation and then rotation transformation, right? Now that needs to be, even that translation and rotation needs to be expressed in matrix form. So that's where what I've done here. So here, this was the previous thing. Already I've given the expression for it. Okay. Now I'm focusing only on, you've got a series of links and joints. Okay. Name the links and joints and then come out with a combined transformation matrix for executing transformation from one joint to the next joint. From ith joint to I plus 1th joint. You will have a combined transformation matrix. If you use that for n number of links and joints, you can get the total number of combined transformations. Right? That's very, very essential in many application areas, not only in industrial robots, in other areas. So that's why this concept has been given. So I brought the information here for the reason that the understanding of DH conventional DH matrix is very, very essential if you're working in the field of robotics. Right? It's a very simple concept. They've given fixed the coordinate system with a particular convention and then they've executed the transformation, right? So very, very, very simple. I can't go in detail about that one, right? It would be much more boring for you people, right? So with the previous this thing, combined transformation, I had the position of the end effector in the three-dimensional workspace for Cartesian